Hi friends, welcome back to yet another session on operating systems. We are into our third module and discussing about solutions to the deadlock condition. The third solution to the deadlock condition is just to neglect and wait till some deadlock occurs. Till then, never bother about what's going on in the system. Anytime we observe that the whole situation went to a standstill, that's a deadlock occurred, then start recovering it. So it is allowing deadlock to occur, so never bother in advance what could happen tomorrow and all that. So let's not waste our time on unnecessarily worrying about what happens next and all that, as we were doing earlier in deadlock prevention or deadlock avoidance. What we can now do is just be carefree, keep the things as they are doing, and anytime you find that the deadlock situation has occurred, then start recovering it. So till then, nothing to worry. Only thing to do is now and then keep watching, is situation safe or in deadlock. If deadlock, go for recovery. If safe, wait for some more time, try again, check is it safe or in deadlock. So that's what the scenario is all about. So here we use two algorithms. One algorithm to examine in what state the system is, to determine whether deadlock has occurred or not. So is the system in deadlock or not is one algorithm. So this algorithm is run every now and then just to make sure that everything is in order. Or if this algorithm says that there is a problem, there is a deadlock, then the second algorithm comes to the picture, then that is trying to recover the situation out of the deadlock. So first one is about detecting the deadlock. So when we are detecting a deadlock, so what deadlock is, it should have four conditions. One, the mutual exclusion. Yes, of course, we cannot avoid that. Second one is hold and wait. Yes, it may be there. And third one is no preemption. And the fourth one is cyclic wait. So to understand the whole thing, we have two situations. One situation where for each resource we have only one type of one instance of each resource type we have. In that case, if that resource is already being locked by some other process, then we need to wait for it. So in that case, we just look at the current situation. So these rectangles are shown by, the squares are shown by, here represent the resources and the circles represent the processes. And the arrows talk about either resource is held by the process or resource is being waited for by a process. So in this case, R1 is held by P2 and P1 wants R1. So P1 wants R1, R1 is with P2, P2 wants R5, R5 is with P4, P4 wants R2, R2 is with P1. So if you look at this, yes, there is a closed cycle. So there are things waiting for one another. So I look for another cycle here. So P2 is having P2 is waiting for R4, R4 is with P3, P3 is waiting for R5, and R5 is with P4, P4 is waiting for R2, and so on. So there is a loop. So instead of talking in this way, you can just make a simpler graph where which process is waiting for who to complete. So if you look for resource R1, R1, R1 is with P2, and if P1 has to continue, it should have R1. So to have R1, P2 should complete. Only after completing P2 its job, R1 will be released. So only after P2 completes R1 will be released, only then P1 gets R1, then P1 can continue. So in other words, I can say that P1 is waiting for P2 to complete, P2 is waiting for P5 to complete, P2 is waiting for P3 to complete, and P3 is waiting for P4 to complete, and P4 is waiting for P1 to complete, and all that. P2 is waiting for this P3 to complete, P4 to complete, and all that. So if you just look at that, instead of getting too complicated graph, we can simplify this graph. So this graph is what we call the resource allocation graph, which resource is allocated to which process and which process is waiting for which resource and all that. But you can just simplify that and say that P5 is waiting for P2. If P2 completes, only then P5 can continue. P3 is waiting for P2, that means that P2 will first have to complete, only then P3 can continue. So here it says that P4 is waiting for P3, so unless P3 completes, P4 cannot take up. For P4 to take up, P1 should complete. For P1 to complete, P2 should complete. For P2 to complete, P3 should complete. P3 to complete, P4 should complete. So there you can see so many loops, and then that way you can say that the situation is deadlock. None of the processes can continue at this situation. So P1 is stopped, P2 is stopped, P3 is stopped, P4 is stopped, P5 is stopped. So what we can do is we can have just a deadlock detection system and algorithm. We just keep looking at what each process are doing. Are they waiting? Are they not? If they are waiting, then is there a loop? If there is a loop, yes, they are waiting. So in this case, all P1, P2, P3, P4, P5, all of them are waiting for one another, and all of them are under deadlock, and hence the whole situation is a deadlock. So that's about a single instance problem. If we can think of a multiple instance problem, it's similar to the earlier banker's algorithm Whittle modification. It can be shown here in the algorithm. So we can just talk about that with this particular problem. So if we see that we have 5 processes P0 through P4, and these are the allocation. 3 resources we have A, B, C, and their instances are already allocated. These are more requested, and as of now none of them are available, so therefore we cannot allocate any new resources now. But can we continue? If you just look at that, we realize that P0 does not require any more. So whatever it is having 0, 1, 0 is sufficient to complete it. So let us say that P0 doesn't require anything, so P0, let's complete it. So P0 completes its job, and this one instance of B is released. Then if you go down, then we realize that P2 also doesn't require any more resources. It has got all it wanted, therefore without anyone's support P2 can also continue. So P2 continues, then after P2 completes, then 303 are released. After P0 complete, this 010 released. Now we have availability of 313 in all. Then the next one, if you look at it, then P3, then 100, we have 313, so 100 can be easily allocated. So P3 takes up, so P3 completes its job, then these 211 are also released, get added to the available list. And then P4 wanted 002, which is also available, therefore P4 also continues, and then comes back, and P1 also is run. So in all, what we can see is first P0 is taken, then P2 is taken, then P3, then P4, and finally P1 is taken. So it can be any other order also we can take up. After P0 and P2, we can go back and work for P1, then P3, then P4. So whatever order you think of. But yes, we can say that all 5 processes have completed, and hence we can say that there is no deadlock identified. But there is a change here compared to the previous one. The previous one, it says that P2 requires 000, but now P2 is requiring 001. Now we have nothing, so we can start with P0, which is not requiring anything, so 000. So then we have released this one of B, but now we wanted one of C, but none of C is available, therefore P2 also cannot continue. If P2 cannot continue, then this 303 cannot be released. If 303 is not released, then this cannot take up, this cannot take up, this cannot take up. So in all, what can happen is only P0 can be run, and P1, P2, P3, P4 all are just stopped there, and therefore P1, only P0 can run, and others P2, P1, P2, P3, P4 are in deadlock. Therefore, we have a deadlock detection which says that P1, P2, P3, P4 are the four processes that are now stopped their execution because of deadlock. So that's how we can detect a deadlock condition. So that's it as of now. Thank you.